Hi, this is Paul again, and I've got a new video to show you, and I'm calling this video Quad Step Phyllotaxis 3D Order Lesson 5. In my last video, in Lesson 4, I showed that spherical geometry of different polyhedrons can be split into perfect segments. Now I'm showing in front that the icosidodeca can be split into 8 segments, and these 8 segments can be split again 4 times, and I'm showing colored balls, and these balls are in a sequence starting red, yellow, purple, cyan, and then back to a red. I'm going to show you this anim in the top view, and you can see that the 45-degree segments or 90-degree segments are lining up to the geometry of the dodeca and the icosidodeca. I'm going to hide the icosidodeca and show the octahedron. Now here you can see that the geometry of the 8 segments are lining up perfectly to the edges and the vertices of the octahedron. Okay, let's hide the octahedron and take a look at the dodeca. Okay, you can see that 4 orbital rings are lining up to the geometry of the dodeca, to some vertices and edges of the dodeca. Now this isn't going to stop here. We also have cubes in the dodeca, so this is showing 1 cube for a start. Now in my earlier videos I showed that there are 5 nested cubes in the dodeca. Sometimes I'm wondering if it is a dodeca or 5 cubes. Okay, I think I'll give it a little tilt and a spin around to show that we have a cube and not a square. So you can see as it's spinning around, it's just like segments of an orange or something like that. Okay, now I'm going to lock the cube and turn the other geometry around 90 degrees. And now we give it a 90 degrees turn in the 3rd axis. I think you can see plain enough that this order will go in many different axes. Now this geometry I call quad step phyllotaxis, and I showed that this geometry will give you the geometry of the pine cone. I showed that those rings with 32 balls could show copies in latitude arrangement. I'm going to bring back some of the work on the pine cone to give you a look. Okay, we'll start with that ring of 32 balls. Now look how them rings are arranged on the pineapple shape. Now you can see that there are 2 helical curves, one starting from the top and one starting from the bottom, 180 degrees about. Now watch when we continue this process. We are making the geometry identical to that of the pine cone. I think it's plain to see that the geometry of the quad step phyllotaxis does the job, and there's no arguing about it. But I guess this 3D geometry of the pine cone produced very little interest. Maybe because it's not abstract art and it's not chaos. Anyways, time is going to tell. So let's get back to where we were. Okay, what I've done now, I've started to focus on this 4-fold system or 4-edge system, and we'll start by going back to the icosidodeca and the dodeca to start. Now first of all, I'm going to move the dodeca icosi to one side. You can see we have the dodeca, and you can see the slimbo nipples of the icosa. Now I'm going to move the icosa out the other side. Okay, the next step is to give it spherical profile rings. Now you can see that I'm using the same diameter for the icosidodeca and the dodeca because they belong together. But I have showed in my earlier videos the icosa is different. It's basically on its own, and the nipples stick out a little bit on the faces of the dodeca, which I call slimbo nipples. Okay, the next step is to give them rings a polar array of 32. Now these 32 rings are basically orbiting rings about the vertical axis between the top and bottom vertices of the icosidodeca. This is very important for the fourfold stuff. Okay, the next step is to grab a copy of the original rings and turn them into red rings. Okay, I think I'll bring the three spheres together again. And then I'll make a copy of the red rings and make 3 rings in the polar configuration. So now we can spread the 3 polyhedra apart once again. Now this 3D geometry of the dodeca and the icosa can be confusing because they have a slight tilt. But hang in there, I'm going to try to show you this. Okay, first I'm going to hide the icosidodeca and show the octahedron. Now you can see that the 3 red rings are lining up perfectly to the edges of the octahedron. So basically the octahedron is the boss when it comes to 4-sided or 4-fold geometry. And don't forget there are 5 of these octahedrons in the geometry of the icosidodeca. Okay, now we'll hide the dodeca and show the cube. Now the vertical axis runs through the top face and the bottom face of the cube. The vertical axis runs to the midpoint of the top edge of the dodeca and not the vertex. We have a similar situation with the icosa. It goes to the midpoint of the top edge and the bottom edge. We'll take another look at this. I'll just show the outlines of the icosa and the 2 golden ratio rectangles. Okay, I've only got one more Platonic solid, that's the tetrahedron, so I think I'll show you this as well. Well, actually I'm showing you the dual tetrahedron, or you could call it the 8-pointed star. Okay, so now I think I'll give it a spin around. Okay, when it's spinning around you can see it much better what I'm trying to tell you, because it's plain to see that you cannot show this in 2 dimensions. And I think it's obvious that people doing research in biology and stuff like that should get away from 2 dimensions because they'll never ever find out exactly what's happening. And I think all these highfalutin theories about chaos is leading everybody down the garden path. Anyways, to the very few people in the world that think my 3-dimensional order is better than chaos, this is Paul saying thank you very much for watching my video.